Hi, everyone. In today's lesson, we're going to revisit equations of lines, but we're going to kind of look at it in a new way in terms of vectors and develop some new ways to describe the equation of a line. So let's get started. So consider here, I've got a little linear combination of vectors. So this kind of like vector equation is saying to get a vector r, you take the vector 2, 2, and you add some scalar multiple of the vector 1, 2. And t is just any real number. So for different values of t, you're going to get different vectors. So let's do 4 of these. So let's plug in t equals 0, 1, 2, and -2, and see what we get for those vectors. We're going to draw each of those vectors on our graph. I'll do my best here on my slide up here. So if you want to pause the video and try that, or follow along with me, or follow along then pause, you can do whatever you'd like. So for our first one, we have 2, 2 plus 0 times 1, 2, which just gives me the vector 2, 2. Vector from the origin to the vector 2, 2. So like that. What if t equals 1? So r would be, and you could probably even do the mental math. I will just break down plus 1, 2, because t would be 1. And we get the vector 3, 4. So 3, 4. I might use dashed lines just to make sure my graph doesn't get too overcrowded. Oh, I drew that first one terribly. Let's erase that. If you were screaming at your screen that I messed up, I caught it, luckily. 2, 2 should be here, like so. 3, 4 here, and again, I'll just use a dashed line so my graph doesn't get too crowded. For t equals 2, we're going to have 2, 2 plus 2, 4. It's going to give us 4, 6. And then finally, for -2, we're going to get 2, 2 minus 2, 4. And that will give us 0, -2. So I'll add those guys as well. So 0, -2 goes down here. 4, 6 goes up here. All right. Now, so what? I've asked you guys to draw a line connecting the tips of those vectors, and you should see something interesting happening. I'm going to use green. I don't have a ruler too in this PowerPoint, so a ruler tool. So I'll just do my best. That seems, I feel like I made a mistake for that one too. 2, 2 minus 2, -4. Oh no, we're good. Just the scale is throwing me off here. So I'm just using, you can use a green dash line. You can use whatever you want at home. And you can see that the tips of these vectors actually form a line, which is pretty cool. And actually, we can state the equation of this line because we have the y-intercept is -2. And the slope, you can read it off. It's from point to point, we're going up 2 over 1. So that would be a slope of 2. 1 of -2, and we have the equation y equals 2x minus 2. So apparently, a little vector equation like we've illustrated here actually gives you a line. Those tips of those vectors form a line. So starting in your grade 9 course, you guys learned ways to describe the equation of a line. So in 2-space, you guys typically had your 2 ways to describe a line. There is a third way that is sometimes used depending on like who your teacher is or what school you're in. So we're used to the standard form or the scalar equation or slope-intercept y equals mx plus b. There is an equation called the slope point equation of a line. I might just show you right now. That should just be y. And I don't really use it. Like y equals mx plus b does the job pretty well for us. But this is also an alternate form of the equation of a line, x minus x1. So if you have a point and the slope, you can write your equation line this way, where x1, y1 is any point on the line, and m is your slope. But y equals mx plus b is kind of a simpler version of that, where the point you're given is just b, the y-intercept. But vectors can also be used to define a line in 2 space. So let's go at another one here. So on that visual, you've got the line negative x plus 2y minus 10 equals 0. So let's get this equation in y equals mx plus b form, check the slope y-intercept, and just see that everything checks out. So if you move everything to the right side, 2y equals x plus 10, and divide everything by 2, you get a half x plus 5, which checks out because the y-intercept is 5 and the slope is up 1 over 2. So let's actually just have a little bit more detail, look at a little bit more detail of this graph. Can you think of a position vector that's parallel to this line? So there's a lot of choices, but I think there's one kind of simple choice here. I'll just grab kind of this section of the graph maybe. If you look at that vector there, the vector that goes up 1 unit and over 2 units, I'm going to draw that down here. So this is a position vector. The vector, I'm going to call it the vector m. And this vector 2, 1. It is parallel to our line. Up 1 unit, right 2 units, you can see is parallel to our line. I'm going to call that m. I'm going to relabel it m up here. And remember, those vectors are equivalent, because to be equal vectors or equivalent vectors, they just have to have the same size and direction. So it doesn't matter where they are. So that vector, it kind of like gives the line some direction. The other thing you kind of need for a line, you need a direction for your line, but you also need like a starting point, somewhere to give the position of your line, so that you can use the slope or what have you to actually draw the line. And so we're going to find a position vector with its tip on the line. And an easy one to see would be 0, 6. And I'm going to call that r sub 0 or r naught, the vector 0, 6. So if you can find a point on the line, or a position vector on the line, and a direction vector that kind of tells you what direction it's going, you can state the vector equation of a line. In fact, we would say that the vector equation for this line would be, paralleling the example we did earlier, we could say this: r equals 0, 6 plus some parameter t times 2, 1. And then we'll say t can be any real number. This is kind of important because it's saying that all these different values for t generate all the points in the line. But if you forget it once in a while, it's not a huge deal. But yeah, this is the vector equation of a line. All you really need is a point on the line and a direction vector. So what does the vector equation look like? Looks like this. R equals r naught plus t times m, where t can be any real number. So this vector r naught is a position vector with its tip on the line. And m is and I'll say a possible direction vector. So just like kind of like slope to the equation, to get the equation of a line in y equals mx plus b form, you needed a point on the line and the slope. To get the vector equation, it's kind of the same thing. You need something to get you to your line, r naught, and then something to give it direction, m. So let's do an example. Let this concept sink in a bit. So we're going to find a vector equation of the line through 1, 4 and 3, 1. And I'll just use a dashed line here. If you have a ruler at home, definitely couldn't hurt. That's good enough for us, I think. All right, we're going to find the vector equation of that line. So the first thing we have to do is we have to, find a position vector that's on that line. And we have some choice here. Anything will do. I know that 1, 4 is on that line, so I'll maybe use 1, 4. For a direction vector, we need a vector that is parallel to that line. Well, if this is A and this is B, then I know for sure that the vector AB is parallel to that line because it's contained in that line. And so a good direction vector might just be the vector AB. And we know how to find that vector. We take the coordinates of B, 3, 1, take away the coordinates of A, 1, 4, and we get 2, -3, which you probably could have figured out by looking at the graph. To go from A to B, you go right 2 and down 3. And so we have a possible vector equation. R equals 1, 4 plus some parameter t times the vector 2, -3. T can be any real number. And that's one possible vector equation. So if you want to write it right now, just maybe think of 2 other possible equations. Maybe one of yours will match up with one of mine. Here's another one. Instead of 1, 4, if I instead have 3, 1 plus t times 2 -3. I'll write that in. T is a real number just for completeness sake. But that also would give me the exact same line. Or if I used the original I had, 1, 4, and maybe use a different direction vector, because I know 2 -3 is parallel to that line, but -2, +3, so taking that that direction vector and multiplying it by -1 gives me another possible direction vector. Both of these equations would generate the same line. And in fact, there are infinitely many possible vector equations of a line because there's infinitely many points in the line to give you r naught, and there's infinitely many direction vectors as well. So that's something to keep in mind as you do work throughout this unit. If a question says determine a vector equation of the line, your answer might be different, but your direction vectors should be collinear, scalar multiples, and whatever you choose for r naught will just be a point on the line. So let's see. Obviously, it's impractical to graph, to keep extending this graph and see if 20 -30 is on the line. But let's see if we can use our vector equation to figure that out. So I'm just going to copy out my vector equation again. So I'll use my original, but you could do this method with any of the forms. 2 -3. All right. So what we want to see is there some value of t that gets us to the point 20 -30? So basically, we're going to kind of solve this vector equation. 20 -30 equals 1, 4 plus t times 2, 3, or 2 -3. Is there a value of t that we plug in gives us 20 -30? If we break this up into its x values and y values, we can, for the x values, we have 1 plus 2t. For that value of t, it needs to give me 20. And then that same value of t would have to give me 30. Negative 30 is 4 minus 3t. So let's solve those two equations and see if we get a value of t that works. So for the first one, I would get 2t equals 19, or t equals 19 over 2. Okay, that's fine. So t equals 19 over 2 gives me 20 for the x coordinate. For this one, we get minus 3t. Negative 30 minus 4 is negative 34. T equals, that would be 34 over 3. And you can check for yourself, but those two are not the same t values. There's no value of t such that this is true. Right? There's no value of t I can plug in here to get 20 minus 30. I can get 20 in the x value. I can get minus 30 in the y value, but not at the same time. So we've just shown that 20 minus 30 is not on the line. Now that was one way to do it. Another way would be, solve the first equation and get 19 over 2, and then plug 19 over 2 into the, the equation for y and see if left side equals right side. It's all kind of the same. All right, so now that we've done an example of creating a vector equation, so again, all you need is a direction vector and a vector that ends on the line. We're going to look at another way to express lines in R2, the parametric equations of a line. So if a vector equation of a line is given by r equals r naught plus tm, I can write this in terms of components, kind of like this. Every point on the line I can write as like as xy, and I'm going to write my position vector as, I'm just going to write it right now as r1, r2. And I'm going to write my position vector as m1, m2. And I actually might actually choose. What do I want to choose for this one? I'm going to choose something different, just to be consistent with my notation I've been using. I'm going to use r naught is x naught, y naught. So that initial point on the line, x naught, y naught. And if I break this vector equation up into an x component and a y component, I get this. I get an equation for x is x equals x naught plus t times m1, and y equals y naught plus t times m2. And these are called the parametric equations of the line. And of course, t is any real number. All the different values of t generate all the points on this line. So at this point, I may slip into not writing out t as a real number all the time. We'll see though. So those are the parametric equations of the line. We call it that because the result is governed by the parameter t. Different values of t give you different points in the line. But it's basically the vector equation just split up into x and y. So let's go back to our example. And the vector equation that I worked with was r equals 1, 4 plus t times 2 minus 3. Let me just double check that. Yep. Okay. And t was a real number. So the vector equations, or the parametric equations, are so easy to get from the vector equations. You just literally break it up. So the first one, x, is 1 plus 2t, and y equals 4. This is the second component, 4 minus 3t. And there you go. Those are possible parametric equations. 1, 4 is a point on the line. 2 minus 3 is the direction vector. We got it. It's that easy. All right, let's do an example where we kind of mix it up and look at a lot of different forms. So consider a line, and we'll often use lowercase l to describe lines from moving this point forward. But here, this is a line. These are the parametric equations of this line. So let's actually go backwards. We have the parametric equations. Let's write out the vector equations. So this is just basically putting the parametric equations together. So I know my initial vector, my initial point in the line would be 3 minus 5 using the parameter t, and 2, 4. And t is a real number. It might just be worth noting here, for this particular vector equation, the direction vector is 2, 4. Sometimes you may want to simplify things. You could write that as 1, 2, and that would be a totally valid way to express the vector equation of a line. And often we will simplify things. I'm going to leave it as 2, 4 for now, but nothing wrong with writing that as 1, 2. So how do we go from these forms, these new forms, back to slope-intercept form in standard form? I'm going to give you one method. So this method is going from the parametric equations to y equals mx plus b, because that is 2 equations, 3 unknowns. And I don't want t's, I just want y in terms of x. So here's what we do. We take that first equation and we're going to isolate for t. So if we rearrange for t, we're going to get x minus 3 over 2. All right, just moving the 3 over, dividing by 2. I can sub that into my second parametric equation, right? I can replace t with x minus 3 over 2. And now t is gone. I've got y equals some expression in terms of x. And I can just rearrange that, clean it up, and have y equals mx plus b. So let's do that. We get minus 5. So we'll have 4x over 2. That's 2x. And then 4 times negative 3 is negative 12. Divided by 2 is negative 6. And I get 2x minus 11. So this is the slope-intercept form of my line. And of course, now that it's in slope-intercept form, I can easily rearrange to standard form. 2x, I'm just going to bring the y over. So 2x minus y minus 11 equals 0. So y equals b. Standard form, I think I just want to be clear. Sometimes standard form, we might also refer to as the scalar form or Cartesian. And different resources use different words for those. In grade 9, you learn it as standard form. The previous text I worked from teaching this course, I think called it a scalar equation, and then the text I use now calls it the Cartesian equation, but they all mean the same thing. I would like to make a note too. The standard form of a line that you guys learned in grade 9, in grade 9 you guys said it's ax plus by plus c equals 0. And all these things, a, b, and c, had to be whole numbers. You guys also had some conditions too. In grade 9 you said you got to do x, then y, then the constant term. And you guys said that a has to be positive. We're going to relax that restriction a little bit. So if you had negative 2x plus y plus 11 equals 0 and had things on the other side, it's okay. That would be fine too. Okay, let's compare. Is our original line L1 parallel to the following line? Well, to see if they're parallel, we need to compare their position vectors. So for L1, I'm going to say M1 is equal to 2, 4. M2, the direction vector for line 2, is 3, 6. And then maybe you recognize they can both be reduced to 1, 2. But maybe you can see that the second direction vector here is 1.5 times the first one. And so since they're scalar multiples of each other, yes, they are parallel because their direction vectors are parallel. All right, one more thing to talk about is this idea of normals, the normal to a line. So when talking about lines in R2, and later it's going to be this idea of a normal will be important when we talk about planes in R3. Sometimes it might be useful to get a vector that's perpendicular to your line. We call these vectors normal. So in R2, the normal of a line is defined as a vector n that is perpendicular to your line. And I will add just a little note here that normals are not unique. Right, in this diagram, this vector n is perpendicular to the line, but a vector that goes down and is a little bit shorter, but that would also be a possible normal. So lots of different possible normals. It's not unique, it just has to be perpendicular to the line. I want to look at a connection between equations of lines and normals. So let's sketch this line. It's in slope-intercept form, y-intercept of 4, slope of -1/2, so down 1/2, down 1/2, down 1/2. And I'll be careful because I'm not using a ruler. You guys at home should probably use a ruler. All right, so there's our line. Done. Can you state a normal to this line? So, the slope is -1/2. And the direction vector for this line would be a direction vector. It might be 2, -1. So you might see a connection there that if you just kind of take the direction vector and kind of rotate it, it gives you the slope, right? So turn 2, -1 and just rotate it like 90 degrees, kind of. If you can visualize that, you get -1/2. A perpendicular slope to -1/2. Remember that from grade 9, perpendicular slopes are negative reciprocals. The negative reciprocal of -1/2 is positive 2/1, or just 2. And if you wanted to get a normal, kind of turning that back, so that's like 2/1, imagine flipping it back the other way, and you get a normal of 1, 2. And you can draw this, a vector, if I draw a vector 1, 2, kind of like that. You can definitely see, yep, those line up, and those are perpendicular to each other. Another way to do that would be to check that would just be to say, hey, is my direction vector and my normal, are they perpendicular? We'll find their dot product to check it out. Here we get 2 plus -2, it's 0. So we know they're perpendicular. So there's lots of ways to figure out a normal. I just kind of talk you through a visualization of a few ways. So we've got a normal. It's the normal 1, 2. Let's determine the scalar equation. So given slope intercept form, we can find the scalar equation easily. We can clear the fractions by multiplying. In this case, we'll multiply by 2. So we get 2y equals -x, and then 2 times 4 is 8. So we multiplied everything by 2. And then I like usually having my x values positive. So I'll move everything over. X plus 2y minus 8 equals 0. And there's the scalar equation, the standard form, the Cartesian equation of this line. So check out the scalar equation we got in the normal. So x plus 2y minus 8 equals 0, and our normal is 1, 2. Can you see a connection between the normal and this scalar equation? And if you notice that the normal actually appears in the scalar equation, good for you. The normal is 1, 2, and if you check out the leading coefficients of x and y, 1, 2, and that actually always happens. The key idea, and we're going to make use of this a lot, is that I'll say for L, for the line ax plus by plus c equals 0, vector n equals ab is a normal. For the line L. So that's pretty cool, and we're going to make use of that a lot, especially when we talk about planes in R3. So let's just do an example based on that. I'm going to show you guys 2 ways that you can get the Cartesian equation if all you have is a point and a normal. So our line is going through 4, -2. So I'm just going to actually maybe sketch this, 4 -2. The normal is 5, 3. So from there, right 5 up 3. Just going to draw that in. So we know that's our normal. This is the point A, 4, -2. All right. And if we want to, we can actually even sketch out the rest of this line. So if the normal is 5, 3, oh, and I was naughty there for sure. I have been saying if we were talking about vectors, we should use square brackets. Some resources use round brackets for vectors too, but I like reserving round brackets for points. So if n is 5, 3, a possible direction vector that's perpendicular to that, the easy way to do that is to switch the x and y. So 3, 5, except if you dotted those, you wouldn't get 0. So you make one of these negative. So 3, -5 would be a good one. So if you can visualize that, so right 3, down 5. So up 5, left 3 would give us a point there. And then roughly drawing my line in. Oh, it's a terrible straight line. Okay, that's all right. That's okay. We don't have to be perfect. But that's just a rough diagram of what's going on in our problem. So we're going to find the Cartesian equation. Let's go ahead and do that. So the first way we can do that is to use substitution. So our Cartesian equation, our standard form, our scalar equation, mixed in all the different ways we can say that in this lesson here, is ax plus by plus c equals 0. We know two of those three things. The normal is 5, 3. That means the equation is 5x plus 3y plus c equals 0. If we knew c, we'd have the equation. And just like back in grade 9, when you guys did slope-intercept form, you plugged in your slope, and then often to find the y-intercept, you'd plug in a point as well. We can do the same thing here, because we know that x equals 4 and y equals -2 satisfies this equation. That point is on the line, so we can plug it in, and we get an equation we can solve for c. We get 20 minus 6, 14 plus c equals 0. So c equals -14. And so 5x plus 3y minus 14 equals 0 is the Cartesian equation of our line. As a little aside, you can maybe just do a quick check to see if the diagram is right. So putting that into slope-intercept form, I get -5/3, x plus 14/3. And this slope is consistent with the direction vector we talked about earlier. And 14/3, that's 4.6 repeated. Definitely lines up with the very rough sketch I did. So everything looks good. But yeah, this was the goal of the question. And a lot of you guys will like that method. There's actually a really cool second method too. And this will help us a lot when we do planes. So the second method is actually to use the dot product. So on my diagram, I'm just going to call this point I made earlier, I'm just going to call that Pxy. And I'm going to draw, just in a different color here, whoops. I want to draw a vector that goes from A to P. Something like that. So if P is just any point on the line, AP is fully contained in that line, right? And because AP is in the line and the normal is perpendicular to that line, AP and N, those two vectors are perpendicular. And what do we know about dot products of perpendicular vectors? We get 0. So if P is any point on the line, then the vector AP, and the equation for AP would be subtracting the coordinates of x of P minus the coordinates of A. So it would be x minus 4 and y minus -2. So that would be plus 2. That vector AP is going to be perpendicular to N. I like using an upside down T to say perpendicular if I'm feeling lazy and don't want to write it perpendicular, which is the case today. So we know that AP dotted with N has to be 0. They're perpendicular. So we have x minus 4, y plus 2, dotted with our normal, which was 5, 3, equals 0. And let's do this. So if we do the dot product, we get 5 times x minus 4 plus 3 times y plus 2 equals 0. 5x minus 20 plus 3y plus 6 equals 0. And we get 5x plus 3y minus 20 plus 6 equals negative 14. And the standard form kind of falls out, giving you the right c value, which is the same as we got before. So I think that method is really neat. And we will come back to this method later on when we get to equations of planes in R3. But I thought that was pretty cool, a second way to find the Cartesian form of a line. So we did a lot today. So we learned about the vector equation. So you guys should know what the vector equation of a line looks like, what the parametric equations look like, and how to go back and forth between them. You should be able to now go back and forth between slope-intercept, standard form or Cartesian form, vector and parametric, and just go back and forth between all of them. Maybe given one, find the equations of all three. And you guys should know what a normal is and how the normal relates to the standard form or Cartesian form of line. So in this section here, these questions are only about lines in R2. In our next lesson, we'll use the same section and we'll talk a little bit about equations of lines in R3. Which of the forms of lines in R2 can be extended to R3 and which ones can't? And then we'll do much of the same kind of problems we did today with lines in R2. We'll just do them in R3. It'll be a bit shorter lesson, but I felt like adding everything into the same lesson would be just too much. So give those a go. I've got practice posted. Hope you guys are staying well. Have a great day, and we'll see you soon.